Oh, hey, how are you? Fancy to meet you. Today, we are going to talk about the Doppler effect. Okay, so we'll be on page 407 in the physics book. Um, the Doppler effect, if I were to summarize it, I would say, this is how I would say it. If I were to summarize the Doppler effect, it is, when you are like standing on the sidewalk and a car goes by you, if you were to picture in your mind right now, what sound does the car make? I want everybody in your homes right now to make the sound of a car going right by you. Okay? Think about that sound in your head. If, like in a movie, a car goes and it's speeding toward you, and then it goes right by you, and then it's speeding off in the distance. I bet most of you had a sound that sounds like this. Like that, right? Correct? Something like that. And or you might even more complicated hear an alarm that goes something like that. As funny as it is to hear me say those things. The Doppler effect is the principle of as a sound is going by you, it goes basically a downward pitch. Think of how now you might not have ever really thought about it, but think how weird it would be if it goes by you. It just doesn't jive well. Think of it going, doesn't sound right, does it? As it goes by you. Going up in pitch doesn't sound right. The Doppler effect makes things go down in pitch. Okay? So, essentially, what's happening is at all times that car is making a sound. And as that car, let me draw a car here. My beautiful car. Every car I draw always looks like an old 80s Dodge Aries whenever I draw a car. I don't ever draw like a modern car. Here's my car, okay? So my car here, what's happening is it's making sound as it goes by, and it's sending out these sound waves. And notice the sound waves are about evenly spread out, right? Well, when, draw you in this picture as well, you are sitting here and a sound wave comes toward you, okay? The car is sitting here and the sound wave comes out, right? And it comes toward you. As it's flying toward you though, okay, here's the first sound wave. Let's say the first sound wave right as it's about to hit you, okay, it took however long to get to you, but the car now it's this close, okay, so it's another sound wave. What's a better way to put it? It's hard to draw as a principle. Picture this. I'm chasing after you, okay, with a Nerf gun. As I'm running towards you, okay, you're standing still. As I'm running toward you, the first Nerf bullet takes 1 second to reach you, right? But during that 1 second, I'm also running closer as I'm firing. And the next one takes, 0.8 seconds to reach you. And the next one, as I'm running toward you, takes 0.5 seconds to reach you. So it's like they are in a quicker progression from one another. Okay, they're like boom, boom, boom from one another. And so it's almost like this. As it is going toward you, I know a way I can draw it. Okay, as it's going toward you, okay, it's flying toward you. The sound waves bunch up. Okay, they bunch up because they are. If the car is sitting still, they would just be sending out a certain amount of sound, like boom, 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 right? Certain frequency, and it's hitting you at that frequency. Okay, once every second, let's say. It's hitting you once every second. But as it's traveling toward you, okay, they're once a little bit less than a second. It's like, every 0.9 seconds or every 0.8 seconds you get hit with one. because the car keeps getting closer and closer. As it's traveling away from you, the first one takes 1 second to get to you, the next one takes 1.2 seconds, the next one takes 1.7 seconds, and so it's a longer distance between them. They're more spread out as it's traveling away from you. Okay, so everybody get that principle that as the sound is traveling toward you, as the object making the sound, I should say, is traveling toward you, the between each successive sound wave, there's a smaller distance because of the fact that it's traveling toward you, right? It's almost like when you're it's like the principle of relative velocity. If I'm standing still and I throw a ball at you, I can only throw it 30 miles per hour. But if I'm standing in the back of a pickup truck and the truck is flying 30 miles an hour, and I throw it 30 miles an hour, it's going to feel like it hit you at 60, right? And so the sound waves are bunched together more when the car is traveling at you, and as it's traveling away, it is spread out. Okay, so how does that relate to the pitch? If you figure it that they're bunched together, it's a higher frequency. They hit you, the sound wave hits your ear more, like at a quicker rate. There's less time between them, so higher frequency. Remember what I talked about yesterday? A higher frequency equals a higher pitch, right? And as it's traveling away from you, it's a lower frequency, and so it's going to be a lower pitch. Okay, they're spread out more. And so really the only place that's accurate is when it's directly in front of you for that split second. It's almost like an auditory illusion, like optical illusions, that like one thing that looks one way but it's actually another. It's like an auditory illusion where it sounds a certain thing. It sounds like a certain thing. As it's traveling toward you, it has a higher frequency. As it's traveling away from you, it has a lower frequency. But the frequency it's actually making is something different than what you're hearing. Does that make sense to everybody? All right. Hopefully it does. That is essentially the Doppler effect. It's why cars sound like they go meow. Maybe we can, maybe when we do our next Google Hangout, maybe you guys can ask me questions if you have any questions about it. Now, here's the equation. On page 408, there's an equation to figure out for the Doppler effect. What you're figuring out in this is there's some sound that's being produced. Okay, there's a sound that's being produced. You're figuring out what sound is heard, not what sound is being produced, but what sound is actually being heard based on the movement of the object. Okay, so what sound is it? So in this equation, you have FD equals FS, and then parentheses V minus VD over V minus VS. Okay, so we're looking at a few things here. Might look complicated at first, but it's not. Let's deal with the V's first. So you have a regular V without a subscript, you have a V with a D for a subscript, and you have a V with an S for a subscript. Actually, let's deal with the subscripts first. There are two different subscripts. You notice one is S and one is D, right? You have a D, an S, a D, and an S. The D stands for detector. The detector is the person who is hearing it. If you're listening, if you're the person listening, you are the detector, okay? The S in this is the source, okay? And the source is the thing that's making the sound. So in that example, a car traveling toward me, I am the detector, the car is the source. Does that make sense? Okay. Now, when we have the V's, VD is the velocity of the detector. I'm listening. Am I traveling? And in every example I've given so far, I'm just standing still, but I could be traveling. I could be driving in a car and listening, and you could, and so you have to input the velocity that the detector is traveling at. Vs would be the velocity of the source, like the car traveling toward you or whatever. And V alone is actually the speed of sound. Okay, I wish there was a different label rather than just plain V, but in this equation, V is the speed of sound. If they do not give you a number for it, use 343 meters per second, because that is the speed of sound in air at room temperature. So 343 if they don't give you something different. Okay? Now you have FD and FS. FS is the frequency of the source. What that means is the frequency that the sound is originally being made. And then what you're solving for is FD. FD is the frequency of the detector, frequency detected. Okay, what you hear. And that's what you're solving for, is the frequency that you hear, or the pitch that you hear. Okay, everybody get that? So you have a FS, which is the frequency of the sound that's being made. You have V, V on the top and V on the bottom are both the speed of sound. VD is the velocity that the detector, the person listening, is going. And VS is the velocity of the source. Now, what's very, very important is that you get positive and negative correct. Okay, positive and negative correct. Some of them are easy and some of them are hard. Here's what you got to figure out. Go off of this one. Okay, I'll just draw a car again. Okay, if a car, go off of this. This is how you should tell, and you should almost draw it every time, or at least drawing in mind. If a car is traveling toward you, that is the positive direction, right? Positive. That's the positive direction. A car traveling toward you, that's going in the positive direction, okay? That's obvious. You'd be, okay, yeah, I follow that. I'm sure all of you follow that, okay? And that means a car going away from you is the negative direction, okay? So toward you is the positive direction, away from you this way is the negative direction, okay? Now, listen to this though, okay? If the source is traveling toward you, positive, source is traveling away from you, negative, okay? Now, what does that mean? The tricky part is, okay, what is it if you are traveling toward the source? Okay, you now are starting to run toward the car. What is it? Okay, so you might have said positive, but it's not. You traveling toward the car is negative. Here's why. Remember I said the car traveling toward you is positive, and the car traveling away from you is negative? Look at the directions, look at the arrows. A car traveling away from you is negative, so that means you going in the same direction as these arrows is negative, and you going away from the car, you're positive if you go away from the car, because look at the arrows. They're in the same direction. You can't have this arrow and this arrow both be negative, okay? So it's based on the source, what the source is doing. If the source is going toward you is the positive direction, and away from you is the negative. And so whatever you do toward the source, it doesn't really matter, it doesn't necessarily matter like east or west. It matters the source coming toward you is positive. So therefore, you going toward the source is negative because it's the opposite direction. Does that make sense? Okay. Got that. Okay, so, and let's do an example problem. You notice it says a trumpet player sounds C above middle C, which is 524 hertz. I'm going to do one example and then I'm going to be done. 13 minutes, not bad. C above middle C, 524 hertz. That is the frequency of the source. 524 hertz. Okay, frequency of the source, 524 hertz. This is the example problem, but I'm showing you. While traveling in a convertible at 24.6 meters per second. Okay, so the velocity of the source is 24.6 meters per second. Now we have to ask ourselves, is that positive or negative? Because if the car is coming toward you, okay, so now that is positive, positive 24.6. The car is traveling toward you, okay? What frequency would you hear? Luckily, you are not moving. So let's go velocity of the detector. You are not moving in this example, so you don't have to worry about that. That's really easy. Okay, is there anything else you need? It says V. What we have V in that equation. What is it? It says assume the temperature is 20 degrees Celsius. That's room temperature. So what did I say you have to assume it is? 343. Unless they tell you differently, it's 343. Okay? And so you input these things. It should be 524. Pause the video right now and try it yourself, although this is the example problem, so whatever. 524, and then V is 343 minus Um, VD is 0, 343 minus 0, and then the bottom part of that is 343 minus positive 24.6. This is another thing I see people get wrong. So this is how it's supposed to be set up. A lot of people will forget this. Like when we make these negative, they will just put one negative there. But on this, when this ends up being negative, it was in the opposite direction. You have minus a minus. This minus has to stay. Okay, 343 minus 0, 343 minus positive 24.6, and you just solve for that, and you'd get 564 hertz. Now, how to check your answer? Use logic. If the sound is coming toward you, it is going to sound higher than its actual sound. What is the actual sound? The actual frequency is 524, right? And you hear 564. It's coming toward you, so it should be higher. Does that make sense? Yes. And it should be fairly close. Like you wouldn't have something that's like 10,000. You know you did it wrong, right? Now, example problem number 6 is a repeat example problem 1, but with the car moving away from you. So seeing all of our work, what would we do differently? Pause the video, try to think about it for a second. What would we do differently, but the car's traveling away from us? Okay, what would we change? Does frequency of the source change? Nope, same thing. Does the velocity of the source change? Yes. Now it's traveling away from you, so it's negative 24.6. Velocity of the detector, no, you're still sitting still, and the velocity, speed of sound is what it is. So here you have minus a minus, so it's still 524, 343 minus 0, 343 minus negative 24.6, and you should end up with something higher or lower? Lower, because it's traveling away from you. And pause this video right now, try to see if you can get it, and pause. I'm back. Okay, so 489 should be your answer. 489 hertz. Let me do one more. I'll do one more, and then I'll leave you. They'll get you guys the rest. It says you are in an auto traveling at 25 meters per second. So this time you're traveling. Velocity of the detector, 25.0 meters per second. Again, we're on number 7. Toward a pole-mounted warning siren. So if it's pole-mounted, what does the source? Does it mean the source is going 0? This time the source is 0 meters per second. If the siren's frequency is 365, so 365 hertz is the frequency of the source. What frequency do you hear? Use 343. So the velocity of speed of sound is 343, and you're solving for what you hear. Okay, this is how I set it up. Okay, and our equation, let's put our equation, FD equals, what's FS should be 365. Okay, FS is 365. Parentheses, top of the parentheses. Okay, so we have the parentheses, top of the parentheses. The first part on the top is the speed of sound, 343 here, and it's minus 343 minus the velocity of the detector. Now, what is the velocity of the detector? It says you are traveling toward 25 meters per second toward a pole-mounted siren. Okay, you're going toward a pole-mounted siren. And what I said, when something is traveling toward you, that is the positive direction. So if something's traveling toward me and this is the positive direction, if I'm going toward it, that is the negative direction. So I put this in as negative 25.0. Okay, 343, and you got to keep that minus. It's not 343 minus 25.0 because that would mean that the 25 is positive. 343 minus negative 25.0, and number 7. And then 343 minus the velocity of the source, which is 0. And so pause this and see if you can get the right answer. Okay. Now, before we get the answer, your answer should be, remember, you're traveling toward the source. What should it be? Whenever you're getting close to the answer should be higher than the original. The original was 365, so our answer should be higher, right? 392. 392. Okay, Okay, hopefully you guys got it. I would like you to do 8, 9, and 10. Have a good night.